Hi everyone, we are here to discuss about Chapter 5, Dispersion, Scattering, Interference, and Diffraction of Light. Dispersion is a separation of white light into 7 color components when there is a refraction of bending of light. White light is composed of different color spectrum: red, orange, yellow, green, blue, indigo, and violet. Each color has its own wave frequency. Different light frequencies bend of different amount when they pass through a prism. When white light passes through a prism, it will refract 2 times, making the separation of colors noticeable. So, as you can see, here the picture example. The white light passes through a pyramid, which the glass prism, and after that, the color appeared. This is what we call the white light separation, and it's 7 color components. The example of this is the formation of rainbow. We observe that after rain, where its hard night passes through a water droplets, so we get a rainbow.
Light scattering is the ability of particles to absorb light and scatter it in all directions. Scattering of light components depends on the size of the particle or scatters. Small particle scatters component of short wavelength, high frequency, while large particles scatter longer wavelength, low frequency. Our atmosphere is composed of tiny particles that scatter the color components of white light and has abundance in nitrogen and oxygen particles, which can be scattered high frequency. They scattered violet the most, followed by blue, green, and so on. This selective scatter is called the Rayleigh scattering. Our eyes are more sensitive to blue frequencies of light, which is why we see the sky as blue. At sunset, sunlight travels farther through the atmosphere. Longer distance would mean that much of the blue light, having shorter wavelength, have been scattered, leaving only yellow, orange, and red, having longer wavelength, to be scattered, resulting to a red-orange sunrise or sunset. Another example is the clouds. Clouds appear white abundance. The water droplets in the clouds are larger than the wavelength of light, which scattered all the color of light. Clouds that contain too much water droplets, like rain clouds, are less effective scatters and more effective absorbance. Thus, rain clouds appears dark. This type of scatter is known as maze scattering and was named for maze scattering occurs when the particles are the same size as or larger than the wavelength of light being scattered. Thus, pollen, waters, vapor, water droplets, and smoke are common maze scatter particles. When a beam of light falls on the atom, it causes the electron in the atom to vibrate. The vibrating electron is turned re-emit light in all directions. This process is called scattering. Earth's atmosphere contains air molecules and other tiny particles. When light for the sun passes through the atmosphere, it gets scattered by the larger number of particles in the atmosphere. According to Rayleigh's law, the intensity of scattered light varies inversely as the fourth power of the wavelength of scattering of light by the colloidal particles is known as the tidal effect. The size of the particles determine the color of the scattered light. This statement can be proved with the help of the simple experiment. Allow a beam of light to pass through a tank of water with a slight mixture of soap and milk in it. If you watch the beam, for the side you can notice that the beam scatters blue light, but when you truly observe the beam for the end, then you will find that the beam is rendered after it has passed through the tank. Since the wavelength of blue color is smaller than wavelength of red color, scatter of blue light by particles in Earth is way large for the reason we see as blue.
Diffraction is the bending of light when it encounters an obstacle or an opening. A shadow is usually formed when light meets an obstacle. The bending of light is not very much noticeable, but when you look around the edges of a shadow, you will notice blurred areas are diffraction fringes. These are the areas where diffraction of light occurs. So diffraction of light means spreading of gares, binding of light when it phases or passes through an obstacle. Diffraction is used to measure stains in materials under load by monitoring changes in the spacing of atomic planes. So the amount of diffraction depends on the wavelength of light and the size of the obstacle. Also, the smaller the opening, the greater is the diffraction of light as shown in the diagrams A, B, and C. The longer the wavelength, the greater is the diffraction of light as shown in the diagram D and E. Diffraction effects are sometimes not helpful when viewing objects on microscope. When the wavelength of light has the same size as the object, diffraction blurs in the image. The wavelength of light is larger than the size of the object. There is no image seen. It means to say, pag magkapareho wavelength of light ngan hit usa nga object or bagay, halata nga blur dito sa nga image or picture. So pag wavelength of light is dako kaysa usa nga object, waray makikita nga picture.
So next, I will be discussing about interference. Interference refers to the combination of waves traveling in the same medium at the same time. So this is the superposition of waves, causing an increase or decrease in the amplitude of the resulting wave. This may combine destructively or constructively in accordance with the superposition principle. The superposition principle says when two or more waves cross at a point, the displacement of that point is equal to the sum of the displacements of the individual waves. The individual wave displacements may be positive or negative. If the displacements are vectors, then the sum is calculated by vector addition. This principle states that when two or more waves interfere, the resultant wave is the sum of the individual waves. If you examine a shadow formed by the diffraction of light, you will see fringes on the edge of the shadow. These fringes, or the interference of light waves, are the result of the diffraction of light at different sides of the objects or obstacle, which causes the shadow to be fuzzy. When this property was observed in the visible light, it was considered as a clear proof of the wave nature of light. So as we all know, light can also be called as wave. So let's say for example, the wave is traveling and then suddenly it travels through a barrier with two holes in it. This is an example of interference. And then while the wave is traveling through the holes, when the wave traveled through the holes already, it will meet up and then it will create a superposition principle. So this is my example. I hope you understand it.
Constructive interference happens when two identical parts of two waves meet, such as a crest of one wave meets the crest of another wave of the same wavelength. This would result in a new wave with the same wavelength but twice the amplitude. You know, if it's constructive interference, if the resultant wave's amplitude is equal to the sum of the two waves. Destructive interference happens when two opposite parts of two waves meet. For example, a crest of one wave meets the throw of another wave, which would result in the cancellation of the two waves. You know, if it's destructive interference, if the resultant wavelength no longer disturbs the medium. The diffraction of light can be shown from two sources or openings. As the waves from these two openings meet, they interfere and produce interference patterns. The bright fringes are the areas where the waves interferes constructively, while the dark fringes are the areas where the waves interfere destructively. Another definition of destructive and constructive interference. Destructive interference is when two waves traveling in the same direction are aligned at the crest of one wave and through of the other wave. The wave will cancel out. Constructive interference is when two waves traveling in the same direction overlap and their crests combine to produce a large wave.